Hi, my name is PJ Jedlovec, and I'll be giving this guest lecture on directional derivatives. So recall from the past that if we take the partial derivative of a function, this gives us the slope in the x direction or the y direction. But we might reasonably ask, how can we find the slope in a different direction? Let's say a diagonal direction. Is there a way we can find that slope? And it turns out there is, and to do so we just take what's called a directional derivative. So what is a directional derivative? If we start by picking a direction, and we can do that by picking a unit vector in that direction, then the directional derivative of a function f in that direction is just given by this formula, where we use the d sub u to denote the derivative in the direction of u of the function f. And we define the directional derivative to just be equal to this limit. The limit as h goes to 0 of this difference of functions divided by h. You might recognize this limit. It's very similar to our other partial derivative formulas, except instead of subtracting two functions where we're adding a multiple of h in either the x term or the y term, there's a multiple of h in each of the terms. And that multiple depends on this a and b that make up the unit vector. That's the direction we're taking the derivative in. So this is the directional derivative. And it turns out this is actually just equal to the gradient of the function dot producted with the unit vector. And so this gives us the derivative in that direction of the function f. So let's look at an example. Suppose we want to find the directional derivative of the function f of xy equals e to the x times sine y at the point 3 pi thirds and in the direction 1 comma negative 2. How would we do this? Well, let's start by finding the gradient, because if you remember from before, the directional derivative is just the gradient dot producted with the direction. So the gradient, if we take the partial derivative with respect to x of this function, we get the same thing, e to the x times sine y. If we take the derivative with respect to y, derivative of sine is cosine, so we get e to the x times cosine y. So this is the gradient of f. So the gradient at this point, 3 pi thirds, we get just by plugging in 3 for x and pi thirds for y in this right here. So we get e cubed times 1/2, comma, e cubed times the cosine of pi thirds, which is the square root of 3 over 2. And so this gives us e cubed over 2 times 1 comma root 3 as our gradient at the point. So this is our gradient. Now, we need to multiply by the direction, but the problem is this v, this vector, is not a unit vector, and we only take the directional derivative in the direction of a unit vector. So we need to change this to a unit vector first, and we'll do that just by taking v and dividing by the magnitude of v. So this is v, and then the magnitude of v is given by the square root of 1 squared plus negative 2 squared. And so this gives us 1 over square root of 5 times 1 comma negative 2. So then this is the unit vector we're going to use. And so using our formula from before for directional derivative, the directional derivative in the direction of v of the function f at the point 3 pi thirds is just the dot product of these two things we've found. And so if we take the dot product of those two, we get the following, e cubed over 2 root 5 times 1 times 1 plus root 3 times negative 2, taking this 1 and this 1, multiplying them, and the root 3 and the negative 2, and multiplying them. And so this gives us as a final answer e cubed over 2 5 times 1 minus 2 root 3. So this is the derivative of the function f in the direction v at the point 3 pi thirds.